This is what can happen to a surface if you have a particle present on the surface. So in the top image here, this is an electron microscopy image of a surface, and you can see there's a particle on that surface with a specific dimension. Now, in our processing, we often will go for a patterning process, so whereby we use a lithography step to describe a pattern on top of the surface, and then we'll use that pattern to transfer the image in the underlying layer through an etch process. Now, imagine that the particle is present there, and we're just going to put a resist coating, and we're going to develop a process in there, and you can see that this particle is blocking the pattern that we're developing on the surface. And subsequently, if we then transfer the surface, we will have non-continuous lines here. This will lead to a failure. If this happens to be the case in the integrated circuit that you're making, then you have a non-connected line or a non-continuous line, and you will have a failure there. That is why, in terms of particles, like I said in the first class, we typically target a cleanliness of the surface equivalent of a ping pong ball on a soccer field. That is sort of the cleanliness that we would like to achieve. We can tolerate at maximum one ping pong ball on a soccer field, but then reduced to a 200 millimeter wafer dimension or a 300 millimeter wafer dimension. Another problem occurs when you have, for example, organic contamination on the surface. This particular case, we have an organic residue on the surface, and we'll take it through a reducing environment such that ultimately, it can convert to a silicon carbide residue on the surface. So reacting with the silicon and giving a silicon carbide image. Now, in order to understand what is happening here, we also have to look at this image here. So this is a cross-section TEM of a silicon substrate on which we have an oxidation process. So we basically inserted oxygens in the silicon matrix, and we would like to achieve a very uniform, thin, in the order of a few nanometer thin oxide layer as a passivation on that surface. What you see here on top is again a silicon that is being deposited, but here it's a crystalline, single crystal structure. Here you can see there's different crystals, so this is a polysilicon layer. But that is not the important part that I would like to describe here. Basically, the oxidation is a uniform conversion of this layer, so that you have one 2 nanometer uniform coating on the silicon wafer. If there's now a particle of this nature, you can see what is happening here. Again, here we have our crystalline surface here, and basically the oxidation process is inserting oxygens in between the silicon layer. So we're converting this crystalline silicon into an amorphous structure like we see here. And if there's a particle here, the oxidizing species are basically blocked from oxidizing the area underneath, and we have the silicon crystal still penetrating in that oxide layer. So if this is an insulating layer and we have a spike of silicon underneath that particle because we could not oxidize underneath, then we have a problem because we will have an electrical failure in that transistor that we make on that area. So you can see contamination can either block a pattern, or it can block oxidation processes and therefore be a risk. There's also a risk associated with the third category of contamination. So we have the particle type residues, we have the organic residues, and then we have metallic contamination. And metallic contamination will also have an effect on the performance, which is more difficult to describe, but you can have ionic charges in that oxide, you can have doping of the substrate. So there are a variety of problems that relate to the metallic contamination. What you need to remember at this point is that there's 3 types of contamination that we have to deal with. So we have particles, the organic contamination, and metallic contamination.